Okay, welcome back for our final afternoon of the fall workshop. We have two sessions this afternoon. The first of these is being chaired by Program Committee member Maurizio, who was also kind enough to run the PGP session. So thank you, Maurizio, for running that. It seemed like it went well. Will you be uploading the keyring? Okay, so the keyring will be uploaded. So I will basically hand you over to Maurizio to chair the next session of presentations.
Hello, hope you had a good lunch. We're going to start this section about root data analysis, and we're going to start with Matt and Dwayne from VeriSign. Please welcome them.
Good afternoon, everyone. My name is Matt Thomas, and I'm excited to be here and talk to you today with my co-presenter, Dwayne, and we're going to talk about caching behavior with respect to root server TTLs. Actually, today's talk is pretty much an extended outtake of a recently published RSAC report. The RSAC Advisory Committee had three main objectives. First, they wanted to kind of look at the current root zone TTLs to see if they are still appropriate for today's environment. And then they wanted to look at lowering the NSR set TTLs and if that actually made sense. And then obviously the follow-up question to that would be if we change those TTLs, what kind of impacts would that have on the overall DNS ecosystem at large? The working party consisted of the people up there listed, many of which are in the room. It's good to see you, and obviously you should talk to all of us if you have any questions. The only other thing I'd like to point out is that the report was recently accepted by the committee and has been published on the ICANN website. I'd really encourage you all to go out there and read it. It's a very well-written document. There's a lot of information in there that we're not going to cover in today's presentation, but I think it's something you would all enjoy. The report itself is actually broken up into like 5 major sections. The first one kind of gives a retrospective view of the history of TTLs in the root zone. And then the report kind of shifts gear to more of an analytic, quantitative kind of viewpoint where we look at DS and NS TTLs in the root zone, and then it looks at the max cache TTL parameter in various implementations out there. And actually, Dwayne's, we'll talk a little bit more about the max cache TTL in the second half of our talk. But the vast majority of today's presentation is going to look at the section of the report that analyzed the diddle data for the extent that recursive resolvers honor TTLs. So I think we all kind of have a theoretical idea of how a TTL and a cache should work, right? And so usually there's a pretty large discrepancy between theory and reality. And so when we went into this report and study, we knew in theory how it's supposed to work, but we were prepared for the real world. And I kind of like to think of the real world and DNS TTLs kind of like this scenario. I'm sure we all did this to our parents when we were younger. We were sitting in the back of the car and we kept asking that annoying question time after time after time, are we there yet? Right? And so we were kind of expected the same thing out of resolvers out there. They're just going to keep asking those same questions regardless if the answer is the same thing time after time. So without that, I thought maybe kind of giving an overview of the data that we actually analyzed so we're all on the same page might be in order. For the purposes of the report, we actually only analyzed DIDL 2014 capture due to time constraints. I think DIDL 2015 was occurring right at the end of when we were wrapping up the report and we just didn't have time. So in 2014, we had 9 roots present. 2015, we had 10. 2014, we had to remove iRoot, and in 2015, we removed both broot and iRoot again. And the reason we did this is because the source IP address in those countries where that data was captured, it was considered PII, and those were anonymized, so it didn't really work for the purposes of our study. Now, we also obviously removed spoofed IP addresses from our analysis as well. For those of you that have not had the opportunity to actually work with the DIDL data, it is basically a gigantic collection of PCAP files that are partitioned in some kind of directory file format on a storage system. Now, unfortunately, for the purposes of what we needed to measure, we weren't going to easily just do one scan over that data. We needed to reorganize it and put it in a much more friendly format. And so to that point, this is kind of what we needed to do. We needed to group and sort the data. Specifically, we needed to group all of the requests by a given source IP address. And then within that IP grouping, we also needed to group for a specific TLD. Here we're talking about delegated TLDs at the time of the DIDL collection. Once we had that grouping complete, we would then need to sort all of the queries by time. Once we had that all lined up, we could start doing our actual measurements. And here we're going to measure the elapsed time between a query within a particular IP TLD grouping. And so for this particular grouping, you might end up with 0 measurements, right? If it only had one request, you might end up with a whole collection of them. So what we elected to use was the median inter-query time delay to describe that data point. I know there were some talks earlier about big data, and I just want to point out that this process sounds very easy, but let me tell you, it is very, very painfully slow when you only have one server and you're talking about hundreds of gigs of data. So I would really like to see at some point in the future maybe the OARC getting a Hadoop platform to enable us to do this kind of data analysis a lot easier. So after we did all these measurements, this is basically what some high-level statistics about the data that came out. In 2014, 2015, we had 8 routes that we analyzed after we removed the anonymized ones. For the particular year, the DIDL data, we actually went and we pulled a historic root zone file to figure out what delegated TLDs were in the root at that time. And we also added rootservers.net and the actual root itself to that grouping just because we thought it would maybe be interesting. But in 2014, we ended up with 106 million IP TLD groupings, and that 106 million ended up with 8.7 billion inter-query time measurements. Fast forward to 2015, that grouping jumped up to 165, presumably because the zone had almost doubled in size in terms of delegations, but we also ended up with 18.27 billion inter-query time measurements there. And just like most internet data measurements out there, this is going to follow a long-tail distribution like we see very, very often. So if we take a look at some of the most basic measurements, here we're going to take a look at a cumulative distribution function of the total number of queries as well as the total number of measurements on a per IP basis for 2014 and 2015. So one of the points we like to call out on the CDF plot is that 65% of these IPs have 10 or fewer measurements, right? So this is already starting to describe the shape and distribution of the data we're seeing, and we're kind of starting to already get a sense of how this interplays with TTL adherence. So the next thing we wanted to do is investigate a little bit further on these IPs. Specifically, how many of the delegated TLDs are they actually requesting? So here we found that on another CDF plot that the vast majority, roughly 75, 80% of the IP space observed is requesting less than 10 TLDs during a DIDL capture. So that's a relatively few number of TLDs given the size of the zone now. So we wanted to see, what are these TLDs that they're actually requesting? So here we're taking a look at a rank ordered plot of the TLDs versus this by the year on a percentage basis. And you can see that, the top 3, we have COM, NET, and the root, and those 3 pretty much make up the lion's share. After that, it kind of falls back to some of what we'll call the original GTLDs, things like ARPA, org, and then after that, the country code TLDs. There was some of a little bit of a significant move between total query volume and COM between 2014 and 2015. But overall, the relative pattern seems to be pretty stable. So what we wanted to do then is also to understand total query volume and how it relates to the actual TTL of the NS record of that TLD delegated in the root. So here we're taking a look at a log-log plot of the total query volume versus the TTL. And it kind of goes to start to show that the TTL adherence here is kind of the exact opposite of what you would expect in a perfect world. In a perfect world, those, on the y-axis, the ones that have high TTLs, you would expect relatively few queries coming from them. And as you move to the lower right, ones with shorter TTLs would have had more queries. Obviously, we don't see that pattern. So the most interesting thing we, though, really wanted to look at was, given those 8 or 18.75 billion queries, overall, what was the median inter-query time over the whole distribution? So here we're going to take a look at another cumulative distribution plot for 2014-2015. And you can pretty clearly see that, what is that, roughly 65%, 70% of the IP request groupings have an inter-time query delay of less than 3,600 seconds or an hour. So it doesn't seem like these IPs are really, or resolvers are really behaving via the TTLs that we would expect them to. But as you move out on the Y or the x-axis there, which is time, you can see some notches in the distribution, right? And those notches actually happen at very specific intervals. 43,200, which is 12 hours, and 86,400, which is 1 day. So we got a little bit more curious to see, is this apply for all TLDs at the root? Does it change on a per TLD basis? And so we kind of created a new taxonomy to put the various TLDs into. So we created a taxonomy of country code TLDs, the root, the original GTLDs, and then all new GTLDs that were delegated, and then we also broke out ARPA. And as you can see, everything except ARPA kind of generally follows that same, distribution with the 2 notches at 12 hours and 86, but it's much, much more pronounced for ARPA. We didn't really dig into it too much more, but we just kind of hypothesized that those are more pronounced due to the way that ARPA is used on the internet. So for our final figure, tying it back to the RSAC report, we wanted to really know as a whole, if the TTLs were to change, what percentage of the overall queries would possibly be affected by a TTL change. So in order to do that, we also needed to include the NXD traffic to the root. And for those of you that have looked at previous publications on the root, you will know that most of the traffic to the root is what I'll call garbage or NXD traffic. And here we saw roughly, and I think this is the 2014 data, it was about 54% of the traffic to the root was NXD. Once we account for that 54% of the traffic and shift our previous CDFs into these various different bins, we can see where the other YXD traffic would line up. There is a little bar on the 86,400. It's just so small you can't see it here now that it's been adjusted for the NXD. It is 0.0001% of total query volume. So we had a pretty clear conclusion out of this that affecting changes to the TLs at the root would pretty minimally impact any of the queries that we saw. So with that, I'll turn it over to Dwayne, and he's going to talk about max cache TTL behavior.
Thanks, Matt. So one of the questions before us was sort of, are the TTLs appropriate and relevant? And one of the things that we looked at was sort of the big public open recursives. How do they behave with respect to long TTLs? Do they limit that or not? So I set up a little survey experiment where I sent queries to all of these guys to a name which I controlled and could control the TTL that was returned and also the content of the R data. So I returned a text record, and in that text record is a timestamp representing the time that the query was received at the authoritative server. And I also have the TTL record that gets returned from the cache. And I know the time that I made the query. And with these three measurements, it can perform some sort of interesting analyses. So this is what the results looked like when we queried the UltraDNS open recursive name server. And you can see on the On the y-axis, it goes from 6 days down here at the bottom to 10 days at the top. So when our experiment starts, records are returned from this resolver with a 10-day TTL, and then it decrements down over time. And then at this point, we stop getting that cached record, and presumably that record expires or is ejected from the cache, and we get a new one. We get a new timestamp in our data. And this repeats, of course, very nicely. It's a little bit, well, you can't really see, but there are actually 8 unique records in this data set. They sort of, they line up exactly. So it looks like there's 4, but there's really 8 separate records that were returned to us from the OpenDNS servers. This is what the DYNE service looked like, and it's very similar. You can see that, again, it starts at 10 days, which was the TTL returned by the authoritative server, but after a day, we no longer get those cache records anymore. They're removed. One thing that's different, though, is that instead of sort of 4 lines, every day, there's this intermixing here where it's interleaved. And there are actually 13 unique responses returned here that are coincidental on the graph. So some of you may be familiar with the different software and how it behaves, and I believe this is sort of the unbound behavior where it returns the original TTL and decrements it until it gets to its max cache TTL setting, which is 1 day, and then it refreshes. This is what OpenDNS looks like to us, and it's very different, of course. There is one record, or maybe a few, that was returned for a very long time. It started out at 7 days maximum, and we saw it for as long as about 3.5 days later. But a lot of them were very short. We saw those records for only very short amounts of time, and there are 148 total unique records. And as you can imagine, this probably has some bearing on the complexity of the back end behind their service and how they load balance and distribute queries to all of their infrastructure. And lastly, this is what Google Public DNS looked like. There was actually 250 unique records, and they do something very different. Rather than the TTL being returned with the original value of 10 days, it's clamped down to something like 6 hours down here. And you can see some interesting patterns here. They start off sort of lined up a little bit, and over time they spread out. I've got a little bit of a zoom in here. This is actually the first 7 hours of this experiment. I apologize, this should say 1 hour instead of 10 hours. But there's something else sort of funny going on here where rather than nice straight lines, we see a lot of variation. And I don't have a good explanation for that, but I have sort of an extreme example from the logs. This is a case where, according to these numbers, this is the time that the response was generated from my server. This is the time that the query was made, and this is the TTL value. And if you sort of do the math on these, the return TTL was something like 5 hours longer than it should have been. Of course, it's still well under the max cache TTL limit of 6 hours, but still there's something going on there that I can't really explain. So, do you want to do the conclusion side, or we didn't talk about this? So a few conclusions from this work. The DIDL data set presented some difficulties for this measurement. As Matt said, we spent a lot of time and effort doing this sorting step beforehand before we could do the actual work, and that took, I think it took something like a week to actually do that. So that was a little bit of a challenge. As far as the report goes, the main conclusions of that RSAC report were that the root zone TTLs seem to matter relatively little to most clients and to the servers themselves. You could change them to a day or less and probably not really impact the amount of traffic that a root name server receives. And as we showed lastly there, that all of the big well-known open recursive public resolvers are going to limit TTLs to, they're not going to serve records for longer than a day anyway. So that was a good confirmation on that. I think we're pretty good on time, so we've probably got time for questions if you have any at this point.
Balvartus. I was wondering if these statistics allow you to see how many resolvers use prefetching. So when the TTL gets near the end, they prefetch it automatically.
So prefetching wasn't something that we specifically looked for. It would be interesting to sort of think about how you could do that with the diddle data. In the little experiment that I did, I didn't see any evidence of that. And of course, when I was generating the queries, it was using dig rather than a browser, which is sort of where you would normally expect prefetching, I guess. But I didn't see any evidence that, well, I don't know. I'd have to think about that some more. Yeah, thanks.
Donovan with AWS. Just curious on the diddle data, did you normalize for like coherent caches with multiple public IPs for the interframe or inter-query gaps? Okay. It didn't look like it would make any difference. I was just curious. Yeah, no, we did not. And for Google, that pattern is what you would see if they were doing something like injecting jitter to avoid coherence in their clients.
Sure. Yeah, that's a good plausible explanation. Yeah, thanks.
Brian Harvick's in OpenDNS. So just wondering, are you guys willing to share the domains that you were querying? Because I'd like to follow up on the results that you saw. I think I know what's going on, but just thought it would be interesting.
Yeah, it's actually so this is a I think it's in two places here. No, it's just here. So it's this. Maybe it's a little bit hard to read, but it's in the slides here. This is a little custom server written with LDNS that. You send it a query and it returns a unique name with a 10-day TTL, and so yeah. And
to kind of answer Paul's thing on prefetching, OpenDNS will prefetch. I can speak for us. I can't speak for anyone else. When it reaches a certain TTL level, but it's got to decrement down to a certain point before we'll do that. So it's like 5 seconds or something. So.
The other Brian from OpenDNS. I can probably speak to a little bit about why we have this kind of very dense rain graph. One of the things that our resolvers do is we have lots of threads. So each of the threads don't lock against each other, but they do lock when they go into the cache. So if they find that something isn't in the cache and they need to do an upstream, then if there are 10 threads in the resolver and they all need to do an upstream, they don't synchronize with each other. So we actually fall foul of a cache record or a queue name suddenly being queried very frequently.
Sure.
And we do prefetching so that if it's queried frequently as it expires, then somebody will get charged with prefetching that record so that the onslaught of query lookups never actually sees a cache miss. But I can't fully explain that. I mean, I'd be interested in sharing your data.
Okay,
and,
yeah, absolutely.
Trying to figure it out.
Yeah, happy to. Yeah. Ray? No, I'm next. Oh, you're next. Okay, very good. Thank you.
Okay, next we have this very interesting analysis using RAIP Atlas for effort with RAIP Belize.
This down somewhere. Oh, it's a bit flat. State control. Hi, I'm Ray Bellis from ISC. Please excuse me if I go too fast. I've just had a double coffee. It was way, way too strong. So, as you may know, I joined ISC back in May. And alongside looking at bind and various other things, Jim Martin, who's here, asked me to take a look at our F-root deployment and see whereabouts we might put some new Anycast nodes in future. And part of looking at that, where we might put nodes in the future, is also, of course, looking at what we've got now. And this presentation will focus on that latter aspect of the research. Now, I looked around to see what data sets were available and found that it's very handily, the RIPE Atlas system already takes a lot of measurements of all the froot instance nodes. There's a particular, in our case, measurement 10304, I think it is made every 4 minutes from every RIPE Atlas probe to the currently selected F instance for that site. They send us the standard hostname.bind.ch text query, and they will then record the response to that query and also the latency of that query. And fortunately, our hostname IDs are quite standard form. We have an IATA code, a site number if we have multiple codes in that city, and an A and a B node as well, so we can tell which of the load balance pair is there. So in this case, AMS1A is obviously our primary Amsterdam node, server A. So there are existing visualizations of this data on the RIPE site, but I found they were a little bit lacking in flexibility. They would always default to go and looking at the A node first. I also wanted to be able to look at historical data as well as real lifetime data. So I spent a few days writing up something with JavaScript and OpenStreetMap so I could produce my own graphs. And most of what you're going to see now are essentially, hopefully, pretty pictures without too much text on them. This is a typical example of what we would see. The red clearly indicates quite high latencies, going down to green. The concentration, if you sort of follow XKCD, you'll see that they say any measurement tends to actually end up looking like a population density map. In this case, of course, the RIPE Atlas probes are predominantly distributed around the RIPE region, hence why in this case there's a lot of data there in Northwest Europe. But more about the actual colors we're seeing here in the global scale later on. So one of the first things I found having built the tool was this. This is our Atlanta node. Curiously, not actually really serving very much in the region of Atlanta, or anything even very much in the same continent. Yeah, so it was quite challenging and unfortunately hadn't been observed before. It turned out to be a very, very simple misconfiguration. Full honesty and openness here, yes, we messed up. We have 3 major sites in the US and lots of sites in Europe where we peer with a particular network provider. But the sites in the US are actually ones where we also take transit from this provider for management purposes. And inadvertently, the froot prefix for all of this network was being announced over the transit link that the 3 sites in the US were taking. So any of our RIPE Atlas probes that were measuring, basically peered through this provider in Europe, will be getting long-hauled all the way to the US, because the local pref on the BGP session says, well, that's a customer transit route, it's got to be preferred over my peering routes. And this was the effect. Essentially, as soon as we fixed this by removing that prefix from our announcements in the US, it was immediately fixed, and all of that red that we saw in Europe went away, and all of those RIPE Atlas nodes in Europe essentially picked a far, far closer peer. Graph doesn't actually show which peer they chose, but the effect was marked, and looking at the overall latency to all of the Atlas nodes, globally it's affected something like a 10 millisecond reduction in average latency to froot. So we're quite satisfied with that. Using the tool, we've also been able to identify things like this. If you sort of look on a daily basis, this is a case where a Latin American ISP was failing to honor our no export community on our BGP announcements. And this particular ISP has a lot of interconnects with Italy and the Balkans, and this resulted in quite a large part of Europe, again, going all the way down to Latin America. Not ideal, and fortunately it's just a phone call away, and that was soon resolved. Conversely, we've had problems where no export can be honored too strictly. We're not entirely sure how this one got fixed, as we tried to report it to them, but at the Polish exchange, they were using a route server where obviously we make our announcements to them and it's multilateral peering. So they then receive our routes, or the other peers are supposed to receive our routes. But in this case, due to a misconfiguration on the route server, we think, they were actually honouring our no export on the route server, and therefore not exporting our routes to all of the rest of the people we're supposedly peering with. The net effect, essentially a node that's there that almost nobody was talking to. This was fixed. And, okay, it's not a particularly heavy node. Hopefully you can see the colours there on the graph. But once that's fixed, yes, we're getting a decent coverage across Poland. In fact, even actually moving west into Germany and beyond. So one of the biggest problems we've had, though, and this is one actually still somewhat outstanding, is what happens if you've got a really, really big popular IX or site where people connect to it just because it is one of the biggest and the best. PIX is, well, certainly one of the largest, if not one of the largest, one of the largest, if not the largest, IXs in the world. Quite a few people connect to that from all over. People in Asia going across the Pacific connect all the way to PIX. Because of ISC's history and who we are and the public benefit nature of the company, quite a few people connect to us over PNIs, private network connects, directly into our main Palo Alto site. So in this case, we're seeing a lot of people who are connecting all the way across to Palo Alto, where ultimately that connectivity is probably doing more harm than good in terms of their connectivity to us. So I'll just toggle between these two slides on and off so we can see the effect here. This is what happened when we withdrew the F-route prefix announcement to AS174. So there was before and after. So again, we've got a fair number of sites all across the world who are now saying, oh, actually, Palo Alto is really not the place to go for our F-route connectivity. Let's go somewhere more local. That's back to that one. Here we've got a close-up on what we see from our Amsterdam node. And clearly the coverage there is good, but what I found actually more interesting on this is not so much what's there, but what isn't there. You'll hopefully be able to see that there's actually some quite significant holes there in the Czech Republic and in Spain. But believe it or not, this is actually not a bad thing. The reason for the hole in the Czech Republic in particular is because they've got really, really good local peering. Almost every Atlas probe in the Czech Republic finds our local node. I don't know what it is particularly about the Czech community, and maybe the Andres here can say something about how maybe it's how the Czech IX is run, and just the nature of the community there, but really, really great peering, and everybody's going right into that node. We did quite a few people from outside the Czech Republic also visiting the Czech Republic node, but yeah, that's what I would count as a really, really good successful site. We've got a slightly different position here, and you look at where politics is potentially playing a factor in this. So our Ukrainian node, and what you notice here is that obviously most Ukrainian sites are seeing the Ukrainian node, and we've got a few up there in the Baltics. But what we don't have is anything in Russia talking to Ukraine. And how much that's due to recent political tensions, we may not ever know. We have similar issues, for example, down in Israel, where we have a node in Tel Aviv, and unsurprisingly, none of the rest of the Middle East talks to that node. They're certainly, I think, prime area for future expansion of RefRoute is going to be large parts of the Middle East. As that node in Tel Aviv is clearly very, very good for the Israeli community, but it doesn't do anything else for the rest of the region. And that's it. That's the pretty pictures done. If you have any questions, please shout up.
Hi, Ray. Sebastian Castro in CRS. Can you go to the first overall map of PODF road?
Sorry, the global one, this one?
That one, yeah.
Yeah.
So that's the global view of, it's a selection of Atlas probes, it's a selection of...
That's a view of every Atlas probe that is supplying data, typically 7,500.
Okay, because that one is interesting because you see a lot of red in Santiago, although there is a local instance of the F-road. You have red in Australia, in the east coast of Australia, and
yes.
there is an F-road in Sydney, and also New Zealand is all red. And there is a
so
local...
in terms of future planning, yes, certainly. I think in Australia, yes, we have an F-route node in Sydney. I think it's Brisbane. So I think Sydney would be a good place to put one in. A lot of the reason also for the red in Australia is because one of the dominant ISPs there doesn't happen to peer with us in Australia, but does peer in Hong Kong.
Yeah.
So they're on the Hong Kong IX, and therefore they're long hauling all the way across the Southwest Pacific to reach Hong Kong instead of going locally. So yeah, the future plan will be a lot more peering, trying to identify all these places where people are going long haul paths when they shouldn't be.
Yeah,
And
okay.
sorting those out, and indeed deploying new nodes to fill those holes wherever possible.
Yeah, I was concerned there might be some skew in the actual data collection rather than in a problem in routing.
Yeah, I mean, in Australia, it's fair to say that because it's actually the dominant carrier in that area, or dominant ISP, who happens to have this peering peculiarity, that makes Australia look worse than it might be.
Yeah. Okay.
And yes, I mean, a lot of these sites are not necessarily completely representative, given that RIPE atlases probes are not so universally deployed.
Okay, cool. Thank you.
Randy Bush, IJ Cryptech. So I'm really cheered. First of all, this was good, Prezo. Thank you.
Thank you.
But I'm really cheered that we've made such a complex mess that it keeps good engineers well employed. But this shouldn't have happened. What did we do wrong, and what can we do differently so it does not require a massive measurement infrastructure and one or more good engineers to hold this together in a reasonable fashion in this horribly even with all these tools, in a horribly manual way. This is embarrassing.
Yeah, BGP is not without its problems.
And you're doing strange routing things because the routing system didn't really do what you needed, et cetera. And
Jeff Houston, APNIC. This is kind of a picture of what is, and the real question, I think, for any cast deployer is what could be.
Yeah.
In other words, you're trying to say, if I deployed in Addis Ababa, what would be the impact on surroundings and distance? Have you thought about how you could bend your technique to look at hypotheticals of what could happen if?
Using Atlas, no, I haven't thought about that too much yet. So much is dependent on exactly what peering relationships you can actually negotiate. Yeah, all the best will in the world, you put a node in, if nobody peers with you, it's not going to do any good.
Right, so I'm saying, is there a way you think that you could take this technique and answer that kind of question?
I shall have to think on that and get back to you some other meeting.
Okay.
Hi, this is Anand from the RIPE NCC. So I have a few things I'd like to add. First of all, in answer to Jeff's question, the probes also do trace routes towards all the root servers.
Indeed.
And so there's all this, this wealth of trace data that could potentially be analyzed to see what AS paths these probes are, traversing, and which ASs are the important ones to focus on.
Yeah.
So, that probably needs a lot more analysis, and it's possible. So that's to answer Jeff's question. The other thing I wanted to say was, Ray, thank you for presenting this. It shows off RIPE Atlas and, all the nice things you can do with it. But I also wanted to highlight one other thing, if you don't mind. Could you go back to the first or the second slide where there's a URL? Yeah, the maps one.
Yes.
So this is just a general heads up to people. If you go to that URL, it does show you instance information about all the root servers and which probes are hitting which instances. And if you haven't realized, you can actually select or click on the instances to narrow down and see which probes are hitting which particular instances. And there's a neat little feature in this called time travel as well, where you can shift the slider and see how things look before and after. And that's a newly introduced feature. So if you haven't seen it, go and try it out and see how, the probes.
My initial implementation actually predated the revamp of the maps pages of about 3 or 4 months ago.
Sure.
Subsequently, I've added the feature on the live version of this where it goes and gets all the current bulk data from live, and then RIPE have a WebSocket API where you can then get real-time streaming of every new event that comes in from the RIPE Atlas network, which is quite funky. So you can actually see the dots appearing in real time as RIPE Atlas probes report.
Yeah, thanks.
Yeah, thank you.
Jim Martin, ISC. To Sebastian's point earlier, when we originally started looking at this, when I asked Ray to look at this, I was looking to try to answer some of Jeff's questions. Where should we put new nodes and that sort of thing? Where should we grow? But the thing that is actually most interesting out of this was that there were a couple of quick fixes, things where there were errors, but also things where we say, really, instead of worrying about deploying new hardware and getting new partnerships, we need to worry about improving our peering, figuring out who it is that we're not peering with, so we end up going, across this subsea cable in the next one, rather than going locally. And so it really has shifted where our focus is to much more of a looking at the peering side rather than just pushing out more and more boxes.
Hi, Shane Kerr, BII. So, I was at a RIPE Atlas hackathon a few months ago, and I was there with some other people who do DNS anycasting. I worked for Dyn at the time. And we did talk about the idea of kind of doing what-if scenario analysis, like Jeff was talking about. And my belief is that it is possible. We have the full routing table. You can use RIPE Atlas to query these locations from a bunch of different places. And you can do BGP you don't have to do full BGP simulations, but you can do partial BGP simulations just as rough hacks. And probably there's tools out there that some grad student used for a PhD somewhere, so I don't know. So I think it's fully possible to do these what-if analysis. I think probably for the effort, it looks like it's not necessarily time for that. I'm also interested that, in my own experience and in yours as well, depeering is a powerful tool to improve your routing situation. But I think fundamentally, also going back to Randy's point, I think the whole way Anycast has been used and deployed is, it was a hack from the very beginning, and it's a hack now. I think it's partially due to the limitations of the fact that we can't add more root servers for reasons,
yeah, we know where you're going.
Partially due to protocol limitations as well, which are much more difficult to address.
In terms of the what-if scenarios, I want to do is refer to my T-shirt, which says, "Does guesswork based on unreliable data provided by loads of questionable knowledge."
Cool. Yeah. Anyway, thank you.
Paul Hoffman. So I'm confused about some people's confusion coming to the mic, because this is about FROOT. So I was really glad to hear what Jim said, that maybe what you learned was not about putting more boxes and such, but dealing with the peering, because you might have a lot of red on that first map, but it doesn't matter to people because maybe F isn't their chosen, isn't closest to them.
In many cases, indeed.
And so,
but sometimes it will be. And
yes.
So it should still be fixed.
I was glad that you focused on those, but in fact, the amount of red doesn't bother me if we had the whole alphabet. Oh, that's Google now. If we had the first half of the alphabet, which is Goog, doing that, it may be that every red dot you had was perfectly okay because there was 2 or 3 greens of other letters.
Absolutely.
So to me, the takeaway is not how does the routing affect this as much as how do we make our routing as good as possible for the places where we expect green only, and everything else, just don't worry about it.
Yeah. I mean,
because if you worry about it, you are going to start messing with the routing tables.
Yeah, I mean, my philosophy on that is, yes, you're absolutely right. These places, particularly France, where we've got this massive clump of red, there will be other root server operators that they can talk to perfectly. But that doesn't mean that we shouldn't try to be the best we can be, at least fix those issues. Because with RTT selection, that sort of thing, there will be times where those recursive servers will be talking to us.
Yes.
And when they do talk to us, there'll be a small amount of harm done because we're not as fast as we could be. So let's get those fixed.
Yep, great, thanks.
Luckily, none of the other servers have this problem.
Well, hopefully we don't all have that problem, Randy.
Well, so yeah, two things to what Paul just said and what people that came before said. what you're seeing basically is not a technical problem. It's a policy problem of the ISPs that are involved, right?
Generally, yeah.
If you look through the maps, several of them, you see a big block of red in France. Okay, like there's a few others.
Yeah, there.
France Telecom, you can talk to them as long as you want, buy them croissant, whatever. They won't peer with you in France. But they have this open transit company that they used to sell transit in Asia, and they'll peer with you there.
Yeah.
Okay, and of course they do. And then suddenly you get an email saying, why are we seeing F-route so far away? Why don't you put one in our network? And then you grab your email archive and send it during the conversation.
Okay.
From months past. And then I guess the guy moved and someone said, why are we paying with these people in France, and nuked it again. Basically, it's a social thing. It's how the business is operated. It has nothing to do with anything technical. The only if you want to solve that problem, someone said, you shouldn't only be worried about who you peer with, in the sense of trying to peer with more people, but also the other element you have to control this stuff is who you choose not to peer with, in any case, if you actually care about these, right? The effect on the end users is unclear, because yes, there may be a better located one for most users, who knows? Maybe someone had their president play golf with the president of the other company, that's how they got their peering, who knows? But it's going to affect everyone. Paul was saying that resolvers tend to lock into their closest servers for a given zone. That used to be true. I don't think it's been true since the Kaminsky. I know that bind was instrumented at the time to make the beans of equivalent
the
times
RTT banding issue, yes.
Much bigger. Otherwise, you would be making which server would be used predictable and easier to attack the connection. So you actually, basically the world is one big place right now for resolvers. And your controls, I mean, yeah, it's nice to know how things are, but it's not a technical problem.
Hi, thank you, Ray. Interesting presentation, Benno Overeinde. In addition to the remarks of Shane, actually, the what-if scenarios and someone working in a university, at the University of Twente in the Netherlands, there's some people working on similar measuring and also monitoring and thinking about what-if scenarios. So we need to catch up.
Yeah,
so it's the SANS project, University of Twente. I can post an email on the DNS OARC for people who are interested. Thanks.
Michael Sinatra, ESNet. There are actually two reasons why you should be concerned about the red dots in some response to Paul's comment, which is the one that people already talked about, which is the sort of social shirking aspect, which is you can't assume I can leave F-route messed up because L-route's going to be fine. That we can't, if we all assume that, we'd be in trouble.
Yeah.
The other problem is that this is a really good lesson learned for the general case of routing and peering an anycasted service. And not all anycasted services have the protocol level failover that the root name servers have. This is actually a good lesson learned for the NOGs, not just for the DNS community, because it's important to understand if you're running anycasted services that you need to be able to realize that anycast isn't going to automatically save your butt.
Yeah, thank you.
Hi, Dave Knight, Dyn. Have you thought about doing any experiments in unpicking your hierarchical anycast setup? So stop doing no export? Because that kind of creates an artificial scarcity in how routes will propagate in a region.
I haven't personally considered that. I don't know if Jim has any comments. No.
We haven't experimented.
Okay. Well, sorry, it is.
I think that's just another face of that we haven't got control of the technology. And we're doing weird hacks to try and overcome routing artifacts in the way we're abusing routing with Anycast. okay? As somebody said, it's a hack, but Shane said. It's a good hack, and we're doing fairly well with it, but we're not scoping it. And maybe the no export's part of the problem. Maybe, I mean, God knows, they've loaded everything else into BGP. You know, go ask for a hack. But I don't completely buy Joao's point. The reason it's a social problem is we haven't developed the technology properly. So therefore, we're relying on the social structure, and it's not going to hold because we're not very good socially. I mean, of course, I don't have any social problems, but it's the rest of you.
Okay, thank you very much.
Thank you very much. That was a pretty interesting discussion. So now we have Jason and Dwayne from VeriSign talking about 13 years of JRoot.
Oh, hey, it's right here. Yeah, use these two buttons to go back and forth. Hi, and welcome to 13 years of old JRoot. Jason Castangwe, you've met Dwayne Wessels. 13 years ago, we renumbered JRoot in order to provide anycasting, get it off the same network as ARoot. And part of the process involved keeping an old J service running for some period of time. And some period of time is still today. So who uses old JRoot? Why haven't they primed? You know, who queries both? What are the unique properties of the clients and of old J? And is it about time to turn it off? So old J has quite the 18-year history. JRoot started being active in 1997 on the same network as ARoot, and as it, in order to break it up for Anycast, this now leaves ARoot and old J on the same network. But we noticed that, changing IP address in the root zone is maybe not as rare as once thought or expected. It's every few years a change happens, and we can see that H is about to. So, looking at old J, we captured a little bit of traffic and looked at some historical data on traffic. All right. So, looked at some traffic patterns, and it's pretty clear that it gets a little less traffic than JRoot. About 40,000 queries per second for J, and 2,900 for V6 J, and about 400 old JRoot. What's interesting to note is that the last line, the Monday here, is a holiday in the States. It's Labor Day. And usually holidays we would get less traffic, and JRoot sure does, but Old J pretty much stayed the same. So that kind of gave us a question or two as, maybe we don't get traffic from the States, or maybe we don't get traffic from people. So you can sort of see the visual of A and J route and the scale difference of the traffic. And so I bring up the scale so you can sort of compare the trends for the days. You can look at the more historical trends, and it's kind of hard to see on the y-axis scale, but Old J gets pretty much cut in half the amount of queries per second over time, and A and J route just take off. We can compare this to change before with D route and how old D route declined a little bit after the switchover of IP addresses, but eventually leveled out at 7,000 queries per second. So with all these queries, we're trying to see, who are these people, who is coming up with Old J, and we had some guesses. Especially older Windows DNS just didn't prime. And so it just took a sample, it took a day, top 1,000 requesters, and just ran FPDNS on them. Got an interesting sample. Only 152 I could find a version, and out of those, 107 are bind, 22 being DJB DNS, and 19 Windows. So it gives us a few oddities. So maybe there's different characteristics that we can pick out, and looking at the fluctuations over the day. But JRoot, about 25% difference over the week. Old J, 28%. And sure enough, they follow the same sort of cascade patterns of a few hosts querying a lot and a lot of hosts querying a little. We'd want this to look a little different, to have something really stand out. So maybe we can find something in who queries both. Now, obviously, we can't really deal with NATs this way, or if there's spoof traffic hitting both. But it seemed a pretty good sort of look at that oddity of who would get the new address and the old address at the same time. And it's pretty symmetrical in terms of how they query. Slight preference if you're querying both as to preferring Old J. You can see the higher cluster of dots. And we have a small little artifact for some internal monitoring. And I think Dwayne's going to continue on talking on some other aspects of what we found.
Okay. Thanks. So the next set of graphs that we want to show is actually something that Jason and his team did when he used to work for Maryland, and they changed the DRoot address. So this was an attempt to sort of mimic something they had done. The idea here is to show, this is going to be another scatter plot, and on the x-axis, we'll show, for a given IP address, what fraction of its queries were an X domain versus non-X domain, no error or non-X domain. And on the other axis, how unique were the queries? Like, were they always querying for the same thing, or were they querying for something different every time? So for the JRoot IPv4 address, you have a lot of data points because there's so many clients. And so the x-axis here is NX domain versus no error. And so to me, these over here on this side, these are sort of the good queries. These are the things that are behaving properly and returning no error answers, actual answers. On the other side, you get all these NX domains. And there's sort of two areas of density here. There's a cluster down here where you've got non-unique names, maybe the same name over and over and over. It's just repeating who knows why. And on the other hand, you've got up here on the top NX domains for things that are always different, random names, or maybe these are attacks or something else. So this is the v4 address of the current JRoot. And if we look at the current address of JRoot for IPv6, this is what we get. And it's obviously very different. First of all, there's fewer points, but there's, you know, almost nothing up here in this corner. There you still get this sort of the good stuff, and you get a little bit of this bad stuff down here. But looking at a graph like this sort of makes me think that you know, those users that end up hitting the v6 JRoot, maybe they represent sort of the good queries, the way we expect DNS to work, the things that are right about DNS, and all the crap, all the garbage ends up hitting just the v4 address. So then this is what the plot looks like for old JRoot, and you can see again we've got some of this which I would call sort of good stuff, but then it's very different than the v6. Whoops, you know, we have this sort of bad stuff up here where we've got these unique names and nothing down here. This table shows the top talkers to old JRoot by their AS number, their origin AS. So they're, you know, it's just and this is covering a one-day period. So in a one-day period, we had almost 4 million queries from a single AS listed there at the top, and you can read the rest of them at your leisure. There's nothing here that would indicate any particular countries favored or overrepresented or anything like that. They're from all over the place, right? So one of the things that I thought might be interesting was when you do when you query like the Team Cymru ASN data and ask it for the AS of an IP address, it'll also tell you the date that network was allocated by the RIR. And I thought, well, maybe those things that are querying the old JRoot addresses are like really old networks that were allocated a long time ago. And so I made this plot. This is actually the current JRoot data. This is not the old JRoot data. This is the current. And on the x-axis here are years, and that year represents the year that IP network was allocated from an RIR. And the y-axis is how many queries we got from that network. And this is for the old JRoot address. And so, you know, I was kind of hoping that we would see something that would maybe go like this, but we don't. We see queries to old JRoot, even from IP address networks that have been very recently allocated within the last couple of years. When thinking about this, we wondered a lot about priming queries. A priming query is, you know, when the recursive starts up, send a priming query, get the current list of addresses. You would expect that to happen, and you would expect the recursive name server to learn the new address of J and stop hitting the old one. So why does that not seem to happen? This is a little bit complicated because the priming query is also the default query for dig. If you just run dig without any command options, it'll do the same thing. So we might be seeing that. This is what it looks like for the current JRoot IPv4 address. And the x-axis here, this is query count, and it goes from 100 to 1 million logarithmically, and I chopped off everything below 100 because you get these sort of distracting moire patterns, which you can kind of see here. There's something interesting going on here right at the 50% line. That means that you know, all of these dots represent IP addresses, and few of them send. Well, this 50% means that for every real query they send, they also send a priming query. There's none that send more priming queries than real queries, which is probably a good thing. But I was surprised that you know, this is up as high as it is. If we look at the V6 data, again, to me this looks a lot cleaner and maybe more normal, but I'm a little bit disturbed by this cluster here. Again, this is the current JRoot IPv6 address, and this is telling me that there are this cluster of client IP addresses that send something like 1 in 5 of their queries are priming queries. That's a lot higher than anyone would predict, you know, based on what we know about how DNS is supposed to work. It's not supposed to work that way. So either these are not recursive name servers the way we think of them, or they are something else. This is what it looks like for old JRoot. And again, we kind of see this, you know, there's not as many points, but again, we see this little smattering of dots around this 20% line. And again, this is just the same data, except it's displayed a little bit differently. This is a cumulative distribution function. For example, this green line, again, is the old JRoot. And the fact that it goes from 0 to 80% along this axis says that something like 80% of the clients hitting old JRoot are not sending frequent priming queries. They're not doing excessive priming. Maybe they're not doing any priming. That's certainly possible. You know, we had some hints that there may be some old software out there that just uses its configured list of hints and never primes and refreshes those. So that could be why this is like that. The purple line is the current v4 address, and the blue line is the current v6 address. And again, this is sort of what I'm thinking is more, you know, the normal or the expected case. The next thing we want to look at is the distribution of query types. So in these three charts here, the top is a JRoot v4 address. This is current JRoot v6, and this is old JRoot. The big red is queries of type A. Next to this orange is quad A. The yellow is NS. Green is PTR. For the IPv6 address of JRoot, this is nice because it's very sort of consistent day to day, which again, that's kind of what we'd expect from a system like this. And again, it makes me conclude that, you know, this is where all the garbage goes that causes these sort of day-to-day fluctuations, whereas this is probably more ideal traffic. For old JRoot, again, we get sort of these variations. But one of the first things you notice is there's a lot fewer quad A queries and a lot more PTR queries. Like maybe 20% of all the queries to old JRoot are PTR queries. It's a little bit hard to see on here, but these sort of greenish ones at the end, these are DS queries, which we see at the current JRoot, and we essentially don't see them at the old JRoot. So the clients that are querying the old JRoot appear not to be doing anything with DNSSEC. This data is also query types. This is from that long-term data. So this is covering many years from 2000 to 2015 with a couple of gaps. But it just kind of shows the same thing. For old JRoot here, you've got a significant portion of, here I think the color assignments have changed, but here the yellow I think is PTR queries, or orange, whatever that is. You can see an attack here, any query, little spike attack right there, 1 month. Yeah, not much more to say about that. So we can also look at the response codes. Red is no error, green is NX domain. For the current JRoot, it's pretty similar between v4 and v6. For old JRoot, actually quite a bit fewer NX domains. This one shows which TLDs are being queried for by each of those groups. So we have .com, .net. The yellow, I think, is .local. And this first green one is actually queries for the root zone. So maybe priming queries and that kind of thing. And this big green one at the end is all other TLDs. So as we said before, for old JRoot, you see a lot of PTR queries, and we would, to sort of collaborate that, we would look for ARPA queries here in this section, and I'm having trouble reading. I think it's this red one or this purple one right there. A more significant fraction of queries in .NET. And I actually didn't do this, but I'm kind of assuming these might be for rootservers.net itself rather than other .NET domains. So I want to talk a little bit about a particular attack event that we noticed last year. This was in the middle of the year or so. And when we were looking at the data, we saw that the old JRoot address was also receiving the attack queries, which was a little bit unexpected. And so I made these charts. Here the colors represent IP protocols. So red is TCP and orange is UDP. And you can clearly see when the attack happens, and the attack was received over both TCP and UDP, which is maybe a little bit strange. And we see the same sort of spike at the JRoot IPv6 address. And for old J, we see a very significant spike in v4, I mean in UDP, but we also see this little spike in TCP. So I think it's very peculiar that we would see an attack hitting the old JRoot address over TCP. This is the attack data broken down by query type. You can see that these were A queries in all cases. And this is the TLD of the query name in the attack. It's probably too hard to read, but it's .com with a space at the end, right? So I don't know if that's intentional or not, but a lot of you have probably seen this kind of attack before, where either intentionally or unintentionally, by mistyping the attack name, this traffic ends up at the root. So all of this makes me think that this attack did not come from spoof sources, or at least not spoof sources talking to us. This came from actual recursive name servers that were doing all the normal things, like some of the queries were over UDP and some were over TCP. Lastly, I've got a quiz for you. So. We did a quick scan of the v4 address space. We sent every address a query for j.rootservers.net. Tell me what the IP address of j.rootservers.net is. So as you can expect, a lot of them answered correctly. I think something like 12 million of them answered correctly. But would anyone like to make a guess of how many answered with JRoot's old IP address, order of magnitude? I need a volunteer. No. Millions, no. So it turns out that it's the 11th most popular answer, 686 answered with the old IP address. But the thing that surprised me was that there was lots of other answers above it, like 20.20.20 and 7.0.0. And some of these have been anonymized a little bit. One of these addresses was actually the source of the queries, so that was fun. And then there's some other ones. There's 10.0.0.1, 128.7.0.0.1. So anyway, it lives on still. Wrapping up. So based on what we see here, I think that the old address appears to receive a mix of what I would call both legitimate and garbage queries. We see a lot more MX spam, TXT and PTR queries at old JRoot. We see about 2 orders of magnitude less evidence of DNSSEC, DNS key and DS queries, and I think that something like this old address can maybe help us learn when attacks are spoofed source addresses or coming through actual legitimate recursive name servers. And the question I would like to put to you, the community, is, do you think that it's better for an old root server like this to slowly fade out over many, many years, or maybe more like the Band-Aid, just rip it off and be done with it? So happy to take questions and your comments at this time. Thanks.
Roy Adams from ICANN. I've got a request, and I did this in private, but I want to do it in public as well. The data captured during DITL, the day in the life of the internet, that all the root server operators do for their root letters. I remember L did it once for their old L root server, and this was, I think, 2007. It would be very nice if JRoot could make this data available from the old root server during DITL for that same period, so you can do a comparative analysis. So that's one remark. Old servers better to burn out or fade away? I don't know the answer to that, but whatever you do, keep on monitoring. Right? So even if you do not respond to queries to that address, keep on watching what comes in. It's just interesting data.
All right.
Thank you.
Thanks, Roy. Yeah.
David Lawrence, and because you didn't mention it, I'm inferring you hadn't done it, but did you ask Henry Schein what was up with their 4 million queries?
No, we didn't.
Okay. Maybe somebody could.
Yeah, does anybody know?
I don't
They've
got a website, so presumably they're contactable.
I've had pretty poor experience with those kind of inquiries in the past, as you probably have. So.
They're a medical services company, apparently specializing in veterinary animals too. Okay. So it really makes the puzzle all that much more complicated. And the other thing on the whole burnout or fade away question, I'm in favor of a little bit of a grace period, but if causing problems is the only way to get people to recognize there's a problem. So I'm in favor of the, give them a few months and then pull the Band-Aid.
All right, thanks.
Paul Hoffman, do we know which, if any, root servers or in which ones have turned off their old addresses when they've done the changes? Because you listed a bunch. Have any of them turned them off?
I can speak to that a little. ICANN kept for roughly 6 months on L. BRoot said that they were keeping something there for about 2.5 years. And when I changed DRoot, it was roughly a year. And then finally just turn the old one off.
And you turned it off so that they were getting, like TCP requests were not getting SYNs, or did you just not respond on port 53?
We ACL dropped, yeah, we dropped that.
Okay. So I think that could be interesting as data for what's going on here, is to see whether, like maybe turn it on again for a day. Again, not with a port 53, but just to see how many things are coming in, to see whether they're still coming. Because it looked to me like these are old lists. These are fixed old lists and such like that. And especially with the fact, with a couple of the things you put in, to me they're Soho devices. And to answer why, in like your second to last chart, why you didn't hear much back, earlier versions of the OEM software, and not just DNS mask, but other ones that they used, didn't have the mistake of acting like a recursive server on the outside. So if it's really old, they wouldn't have been doing that, and yet still doing the crap that we see.
Right. Yeah. Robert Edmonds, Farside Security. Did you, by any chance, analyze the distribution of UDP source port numbers?
No, I didn't think to do that, but that would not, I mean, we have the data, we could do that.
That might
Yeah.
reveal
Yeah.
if it's, port 53, it might be a resolver, or if it's an ephemeral port,
Yeah.
you might be able to infer what OS it's running.
Yeah.
And on the better to burn out or fade away question, have you considered intermediate things like returning ICMP port unreachable, or introducing like artificial additional latency, stuff like that?
We haven't really considered that. I think the sort of the way we've approached it is, maybe Jason can answer this too, but after 13 years, it's kind of become a bit of a hassle, and maybe our lives would be simpler if we just stopped listening on that address totally. Is that?
Yeah, I'm in much favor of this.
Thank you.
Hi, Roy Arends, ICANN again. Two things. What Robert just said. Another thing to look at is the RD bit and the identifier randomization or non-randomization that might give away the client who's behind all this. The second thing I just thought of, and you probably know already this, but you don't have to have the old J root as a hint in order for any resolver to ask the old J for data. So one way I could do this is, for instance, have in the glue address data, list the old J root. Have you counted that out?
I've seen that in the past. I've seen examples of that exact thing in the past, but I didn't pursue that for this talk. So that would be interesting to also follow up on and yeah, see if we can do that. I think some people have databases that can help us with that.
Yeah, Farsight something. Yeah. Cheers. Thank you.
Matt Weinberg, VeriSign. Being on the hook for operating old JRoot, I'm definitely in favor of the burnout option. Maybe we should all hum and see if we want to get rid of it.
Sorry, I may have missed it. You said that you're seeing more MX, TXT, and PTRs. Have you done any correlation for the IP addresses requesting information from the LJ root against known sources of spam? Like, have you, DNSBLs, for instance?
No, I didn't do that. That would be interesting. Yeah, I would. I guess we could do that. I mean, that would sort of mean that the spam engine is also the source of the queries.
I was thinking like a botnet.
Yeah.
The entire thing is encapsulated and look at the whole thing.
Yeah. Right. All right. Thank you.
Okay, thank you guys. That was really interesting. We have one small talk outside of the program. We're going to invite Chain Care to talk for a little bit. I don't know if he has slides, I think not. After that, we're going for a coffee break. So, welcome, Chain.
Great. Hey, well, I want to thank the program committee for giving me a couple minutes here. I kind of flubbed up my presentation proposal, and so it wasn't on the normal presentation slot, but they said they'd give me a couple minutes to talk about a project I've been working on. So this is about the Yeti project that I've been working on recently with BII and a few other people. So if you might have seen a presentation if you were at the last IETF. I was at the IPG, and I gave a very exciting, I got a lot of exciting feedback to the presentation there. So luckily, we don't have enough time to get into it very deeply right now. But basically, what the Yeti project is a root server testbed that Paul Vixie came up with the idea at the Wide Camp, talking with Akira Kato and my colleague, Davey Song. And so the idea is to set up a root server testbed. The problem statement is that there's a lot of interesting behaviors and tweaks and changes that we might want to do to the root server system. But of course, it's so crucial to the operation of the internet, we can't really do anything to it, period. So We want to create a system that we actually can do some experimentation there. So that's the basic idea. So what it is an IPv6 only test bed. Right now we've got 12 different operators who run their own Yeti root server. And what they are presenting is a copy of the IANA root zone. We take that, we strip out the DNS signatures, we change the NS OARC set in there to the 13 Yeti root servers, and then we re-sign it with our own key and publish it. So that's the whole process. And then we've got 13 different servers right now. We're adding more, and we have no particular hard limit for the total number of servers that we're going to be running. If it's quite easy to do, you can do it in a virtual machine. We have a web page which talks about the requirements. We've recently refined the process for it. So if you're interested in joining the project, you can run one too. And right now we have a bit of a hard time getting query traffic to it, obviously. You basically just need to update your hints file if you want to participate as a resolver in this experiment. And we have a few options that we're doing to make that stuff work well. We worked with one of the local universities in Beijing, and they're sending query traffic using the Yeti as their root. That's only a few queries a second on average, though. Because of caching, it's quite difficult to get lots of queries, and we have some ideas that we're using to do that. So the idea is we've got this infrastructure, we've got something that resolvers can query to. It serves up the normal DNS. You can just use it day to day. The whole point of this is so we can do experiments. So we've been spending the last couple months stabilizing the network, making sure that we have processes and monitoring and all these kind of normal things. We kind of did it in the traditional VXI way of ready, fire, aim. So we spent the last couple months aiming and building up the infrastructure and things like that. So we're at the point now where we're about ready to start our experimental phase. We've got a whole bunch of different experiments that we want to run. We've got an experimental protocol. So we're going to try to do it at least with a thin veneer of science. We're going to document the experiment we're going to run first, do it in a lab first, make sure that it works, go through a easy approval process, and then put the experiment into the production network. So an example of an experiment that we might want to run is to move to a TCP-only version of root system where we truncate every bit to see what the impact of TCP-only at the root would be, this kind of thing. We want to experiment with rolling the KSK, doing algorithms rolls, trying different lengths of key signing, all these kind of tweaking the different knobs of the protocol and see what breaks and what doesn't break. Yeah, so that's the basic idea. And like I said, we're ready now. We're about to start our experimental phase, and I'm quite excited about that. So one of the first things I think we're going to look at is we're probably going to try a version of the ICANN KSK role proposal, which I think is complicated and danger prone. But we're going to try it and make sure it works, for example. So that's the basic status of where we're at and what we're doing. Now we realize that because this is about the root server and because I work for BII, which is the Beijing Internet Institute, a Chinese company, there's a lot of suspicion and concern about where we're going politically with this. I have to admit that talking to various people directly for the past several months since I've been involved with this, there has been a lot of confusion among even the participants about the goal. As I said, it is an experimental network. We've had people who want to put large customer bases using this, and I've had to explain that we're about to break stuff, so you really don't want to do that, even though it would be great for the project because we get lots of traffic. So a lot of people view it as a prototype network. It's not a prototype, it's experimental. We're going to break stuff. But nevertheless, the political questions about playing in the root space are there. My own take on it, especially at a meeting like this, is that let's just focus on the technical stuff and not worry about the political issues. And I think that's about it. I needed to be brief so I could fit in before the coffee break. We're going to be having a workshop the Saturday before the ITF in Yokohama. So if you're going to be there, or if you live in Japan or someplace near there and want to stop by for a half-day workshop, that would be awesome. It's going to be focused on the Yeti project itself, of course. So we're going to have hopefully as many of the current participants and maybe possibly future participants attending as possible. It's not going to be limited to that. We're also going to talk about any other kind of root server issues or DNS issues around the root server system. So if you're interested in that or have anything that you want to say about that, you're welcome to come, and we really invite everyone to come and join and engage with us. And I think that's about it. I'm here for the rest of the day. Come and talk to me. I want email, stuff like that. That's it. And again, thank you for letting me come in at this last-minute ad hoc way. I appreciate it.
Thank you, Jay. Okay, the coffee's here, so I won't detain you. Also, watch out for the cakes. There's now a box at the registration desk, so you can dump your badges on the way out. Please fill in the survey. The URL's there. We'll put it on the event homepage as well. We'd love to hear what you think about the presentations and about the logistics, so we can keep making the meetings better. You may have seen some of these flyers. We'd really like to sign up some sponsors for next year's workshops. If you commit today, or if you commit to more than one workshop for next year, we can offer you a deal, some discounts. So please speak to Dinesh if you'd like to do that. NaNog registration is open between 4 and 6 this evening, so you might just want to bear that in mind if you want to get to their social, which may need a badge. Other thing is PC have done a great job. We review the composition of the PC. We'll probably have at least one PC seat vacant for next year. Basically what the board does between now and the end of the year is figures out who's going to be in the PC for 2016. If you're interested in serving, please speak to any board member, and we can start including you in the process for deciding that. And that's it. Basically, we will resume from coffee at 4 p.m.